So unfortunately, the first lecture of this series didn't manage to capture on the day, and so I'm going to try and do my best to replicate that just on this kind of podcast. So I'm sorry if it's not exactly what matches to your notes and exactly what I said. I need to start off with the important thing in that these lectures are usually, hopefully, being panoptoed. There's an irony here in that I did all of this and then they didn't capture. But if anyone has objections, if they could please let me know. Then I went on to talk about the recommended texts. And this book by Wardle, we have as an ebook, which means that everybody can access a copy. But if you find that you're liking this photochemistry and want to read further, I would recommend Turo. It's a really, truly excellent book. But if I was to be asked the single kind of best book to get people into photochemistry, I would recommend this primer by Wayne & Wayne. The primers are basically designed to match people's lecture courses. It is a lecture course amount of material. Therefore, this primer is kind of a perfect amount of material. It's not too much, it's not too little. It is a Goldilocks book. It's got some really interesting things in it, and it's really well kind of presented for the novice reader. So I would highly, highly recommend the Wayne & Wayne. But the Wardle we have as an ebook, which means that everybody can get it. The Wayne & Wayne, there's a lot of copies in the library, and the Tiro, there's just one or two available. So, what are you going to learn? Well, the course is split into two sections. You get a few lectures with me, and then hopefully a workshop, a few lectures with Frank, and then hopefully again a workshop. I'm going to be talking about the more kind of what I would call the photophysics of the situation, the kind of looking at what's going on in terms of the absorption and the emission of light, what's happening with the molecule, whereas Frank's going to talk much more about the chemical processes of what's going on. So he's going to talk about things like photography and photosynthesis, and things like how the eye works and things like that. So that's the kind of the difference. As I said, you get hopefully 6 lectures off me and a workshop. I might bleed into that lecture 7 and I'll only have a half a workshop. I can always book extra classes if you want. So, in lecture 1 we're doing the absorption of light, we're doing things like the Beer-Lambert Law and the Franck-Condon Principle. These things you should be fairly familiar with, but hopefully we're going to take them to a slightly deeper level. I included this table here, which is just to help you convert between energy units, particularly when people are talking about things like semiconductors. They will use this unit of an electron volt. And so being able to think about the electron volt in terms of wavelength is really, really important, or indeed in our more usual kilojoules per mole. So I've kind of used these words photophysics and photochemistry already, but as a photochemist, I kind of split the area into 3 different sections, and I do all of them as a photochemist. The first is the spectroscopy. That's very much about the technique, how you go about measuring something. And we're not going to discuss that at all in this course. Then we have the photochemistry, which is very much the reactions, the molecular structure, and the photophysics is the bit that I would term in terms of the thermodynamics, the kinetics, the quantum mechanics. And so, perhaps just go in this a slightly deeper level, in that photophysical processes are transitions which convert between excited states or between an excited state and a ground state, whereas your photochemical reactions are very much kind of molecular rearrangements, molecular reactions, which occur as a consequence of an excited state. I will be talking about the form of the photophysics. Frank will be talking about the latter, the photochemistry. When I say photophysics, this is not kind of traditional physics. This is very much still chemistry. It's just the words that we use. It's to kind of define the difference between the two very, very different areas. So part of the thing with photochemistry, there's a huge amount of nomenclature. You will recognise most of these words already. Some of them you won't, but we will be talking about them, and it's kind of just really useful to gather together these kind of strange words because you're going to have to become familiar with them. So, let's start off. Well, what is our view of the world? Well, our view of the world, you kind of learnt this in first year, is that everything is quantized, whether that's electronic energy levels or vibrational energy levels or rotational energy levels or translational energy levels. They are all quantized. And the way the world works is the translational levels very, very close together. They almost appear as a continuum, but they are defined energy levels. Then we have our rotational energy levels. It's quite easy to rotate a molecule. It's quite a low energy process. And the rotational energy levels are occurring down in the microwave region of the spectrum. Next up in energy is our vibrational energy levels. Vibrational energy levels are occurring usually in the infrared region, and then the highest kind of energy levels within a molecule are our electronic energy levels. This is movement of electrons either between like the different orbitals, and an example like hydrogen atoms, or between the bonding and anti-bonding orbitals or non-bonding orbitals in our molecular model of the world. The thing about these electronic energy levels is they're occurring in the visible part of the spectrum. Now, that becomes an obvious statement when we learn a little bit about the processes that are going on, and Frank's actually going to talk about some of the chemistry of the eye. But the idea is all of these energy levels are quantized. Because they're all quantized, they're following the Maxwell-Boltzmann distribution. And this tells us about the populations at different levels. And for translational levels, we have a large number of different energy levels populated. For rotational, we've got a few. Vibrational, we might have a few molecules in an excited state. But for electronic energy levels, if we actually put the numbers into this Maxwell-Boltzmann distribution, almost all molecules are in the ground state at room temperature. It is a ground state kind of world. Everything exists in the ground state as far as our view goes. It's a pretty good model because they're very, very, very small numbers. They're only in the excited state. So we can simplify our life. Unlike previously when we've perhaps had to take into consideration the Maxwell-Boltzmann distribution, we don't. So we don't have to worry about kind of this here is a speed thing, but it could be a temperature thing. This is measuring the speed of the molecules and the populations of them, but we could equally replace the speed with the energy. And this is the temperature, but we can look at the other variables that are affecting it, like the energy gap and things. So on the day, I brought in 3 different solutions. I will post a photograph of them along with this slideshow. But the gist of it was I had a very, very deep blue. This is this one on the left. It's called methylene blue. It is specifically designed as a chromophore, so to be strong in colour. Has some really interesting chemistry with it as well, but it's designed as a chromophore. The second one is our very common oxidizing agent, potassium permanganate. Potassium permanganate is kind of a rich deep purple, but you can see that it's nowhere near as intense a colour as the blue. And finally, I had the copper complex, the hexa-aqua copper complex, which when we laid them all next to each other had absolutely kind of no discernible colour. We're all used to seeing copper 2+, copper hexa-aqua 2+, as a rich blue colour, but that's only because the concentration is so high. These were all 2 millimolar solutions. I made them all up to be the same concentration, and we can just see how weakly absorbing some of these transitions are. So what I wanted to talk about in this first lecture was very much what makes something a good absorber of light, what makes it a weak absorber of light. So I've got my energy levels. Well, I'm not going to spend a huge amount of time talking about atoms. So this is a difference between the course that I'm teaching this year and perhaps previous courses. Previously we've talked about atoms and molecules. I have decided that there is so much to say about molecules, I don't have time to talk about atoms. So almost everything I'm going to talk about is a molecular view of the world. So if we look at our molecule, we have different types of orbital, different types of energy level associated with those orbitals. So we have our sigma bonds and our sigma antibonds. And usually when we're talking about absorption and emission of light with these compounds, we're not particularly worried about sigma bonds and sigma antibonds because the energy gap is too high. We're more normally concerned with what's going on with these pi bonds and antibonds and these non-bonding orbitals. So if I have a heteroatom, I will start to introduce these N to pi star transitions. If I have no heteroatoms, I just have pi to pi star transitions. And my transitions are going from my ground state, which is my HOMO, my highest occupied molecular orbital, and I'm exciting the electron into usually the LUMO, the lowest unoccupied molecular orbital. I could also have a case if I had a radical where I had a singly occupied molecular orbital and I could just absorb the one electron between the SOMO and the LUMO. But I'm not going to talk hugely about radical species. I just thought I should mention that SOMO is also a term that we come across. So I've said about this pi to pi star transitions, and this is just a series. I've got butadiene here, and I'm just increasing the amount of conjugation. So if we take my top molecule here, I've got 2 double bonds, I've got 3 carbon-carbon bonds in total, and we can see this absorption of a wavelength of 217. 217 short wavelength is giving me a high energy transition. As I increase the amount of conjugation, I'm increasing the wavelength, and therefore I'm decreasing the energy transition between the 2 molecules. Interestingly, I know that in our kind of traditional view of the world, between the top molecule and the second one, we would say, well, actually, it's still only 2 double bonds, but we've got to think about the bigger kind of picture of the molecular orbital. These energy levels are spread across it, so it's a small difference in the shift in the wavelength, but that is because the bonding is not simply as simple as where we put it, and you can actually take the knowledge that you have from Professor Steve Parker's lecture notes and work out the molecular orbitals in those cases. Here we have no heteroatoms, whereas my next case I've taken some examples of heteroatoms, and I've shown both the pi to pi star and the N to pi star transitions. Here on my top one, I have just the 1 double bond, and I have the lone pairs essentially on my oxygen atom, and I can see the 2 transitions, one at 270, the higher energy transition at 187 is the pi to pi star. And again, as I increase the overall conjugation in the molecule, I decrease the energy of those transitions, I increase the wavelength that these transitions occur at. So, I have my energy levels, I have different allowed kind of spin arrangements of my molecules. So if we go right the way back to first year and we had our Hund's rule and things pairing and all of that type of thing, if I pair electrons in an orbital, 1 up, 1 down, my overall spin multiplicity is 1, because I'm taking my individual spin components from my electrons, and I have a plus a half and a minus a half. The sum of those is 0, plus 1 gives me my overall multiplicity of 1, and we refer to that as a singlet. If I instead had 2 aligned spins, so this is my case, I've kind of shown my arrangement of my electrons here in this T1 state, they're both spin aligned. Because of something called spin correlation, it's a lower energy, and we'll discuss that a little bit more later. But my overall spin multiplicity in this case is given to me by my plus a half, multiplied by 2, and then add 1, and that gives us this 3, and this is why we refer to it as a triplet state. So my singlet states, I'm using the shorthand of S to label them, my triplets, the shorthand of T, and we can see here that my ground state I've labelled as S0. This is my ground state, this is my HOMO, my highest occupied molecular orbital. And then I'm just increasing that integer value every singlet state above this. So my S1 is the lowest excited singlet state. My T1 is the lowest excited triplet state relative to my ground state orbital. We can have a doublet, again, where I was talking about these SOMO species. We can have a doublet, and the same rules apply. 2 times a half is 1 plus 1, and that gives us our doublets. So, triplets. Why are triplets lower in energy than our singlets? Well, we know that if we go back to first year again and we use Hund's rule, we know that the idea of Hund's rule was that if we put our electrons in different orbitals, all with their spins aligned, they were in a lower energy state than when I started to pair them. We kind of use these kind of hand-wavy, slightly chemistry arguments. Without, there are kind of deep-seated physical reasons why this happens. But the gist of it is that we see greater electronic repulsion between the electrons when the spins are aligned. And therefore, when I say aligned, I mean paired, one up, one down. And therefore, we see a higher energy state. When all of the spins are in the same direction, this is minimizing these repulsions, and I see a lower energy state, which is why triplets are always lower in energy states than singlets. One thing I will say at this point, almost all of my figures are going to label my singlet as a ground state, but there are certain molecules that have a triplet ground state. In fact, one of the molecules I've shown you today, this very rich dark blue sample, the methylene blue, has a triplet ground state. So they do occur. It just depends upon the structure of the molecule. So back again to kind of your first year knowledge and starting off with the Beer-Lambert Law. So the Beer-Lambert Law is basically relating the intensity of the light that passes through a sample to some properties of that sample. So the length that it has to travel through, that seems pretty obvious. The further it travels through the sample, the more light will be absorbed. And the concentration, the higher the concentration of the sample, the more light will be absorbed. But we have this constant of proportionality, this epsilon. So I've shown it in the transition, but if we just think about it in terms of the absorption, this constant of proportionality, this epsilon, is clearly a really important thing. It's telling us how much light is absorbed. But what factors are influencing the value of epsilon, and what factors are limiting our validity of the Beer-Lambert Law? Well, it only works so far, in that it doesn't work if we've got a lot of scatter. It says that the absorbers must be acting independently of each other, which means that they need to be far enough apart that the electric field isn't influencing what's going on. We must start off with collimated light in. The light in has to be monochromatic for the Beer-Lambert Law to work. This monochromatic light is less of an issue in molecular stuff. In terms of my absorption bands are normally very, very broad, hundreds of nanometers. But the validity of the Beer-Lambert Law in gas phase spectroscopy, so things like atomic absorption, becomes increasingly complicated because of this light needing to be monochromatic, which is why we have to match the source of the light and the sample. That's kind of going a bit more into the spectroscopy of it. But one of the kind of most simple things that we can think about in terms of our molecules is we want to make sure that we're measuring the absorption of the thing we think we're measuring the absorption of. we want to make sure that we're measuring the absorption of the ground state, that we've not excited everything just because of the sheer flux of light coming in. Everything's not in the excited state, and therefore we're seeing an absorption of that. We want to make sure that the molecule isn't kind of dimerizing or forming aggregates in any way, because then we're not measuring the absorption of the thing we think we are, and they'll have effects. So just going into the Beer-Lambert law, we see this exponential decay of light passing through it, and it seems perfectly sensible that the more path length I go through, the more light is absorbed, the higher the concentration, the more light is absorbed. But what becomes increasingly important is what is the origin of this epsilon, and largely that is what I'm going to talk about, this origin of this epsilon value. Well, I'm just going to take a little step back and just remind you a little bit of your vibrational spectroscopy, because, okay, we've got a light absorbing, but exactly what's the process that's going on? So when we had our vibrational spectroscopy, we had a Morse curve, and we had our vibrational energy levels, which merge as I go to increasing level. The gap between them becomes smaller. The reason for this is it's an anharmonic situation, or it's non-symmetrical. It becomes harder to push them together. Eventually the repulsions become really, really great, and eventually when I pull them apart, it's not like a perfect piece of elastic, they'll snap apart and I'll break the bond. That's the process of what's going on. And I have this equilibrium position. So my equilibrium position is basically the position at this bottom of the well. Now, why have I backtracked? By the way, all of these equations down the right, this is explaining what's going on, but it is not, I do not expect you to use them or remember them. It's just to explain the maths of this Morse curve. So why do I care about this? Why am I kind of backtracking a little bit to vibrational spectroscopy? Well, the truth is I'm not, because the gist is that my ground state has one of these potential wells, but so does my excited state. For a bonding orbital, it will be a potential well. And my transitions between them are going to happen very, very fast. So my excited state orbital might have a different equilibrium bond length, a longer equilibrium bond length, a longer kind of a change in structure. So I see this shift in terms of my reaction coordinate, but my transition is happening very fast. It's not allowing the molecule time to rearrange. So we express it as a vertical line. This is called the Franck-Condon Principle. So when I'm going between a ground state, which is my lower of the two here, and an excited state, the upper of the two, the transition is a vertical line between them. Electrons move between energy levels in a very, very quick manner on the femtosecond time scale, whereas molecular vibrations are on a picosecond time scale. So there's no chance for the molecules to rearrange. And so we end up with a pattern where we are exciting not into usually this kind of ground vibrational state, but usually into an excited vibrational state because of the overlap, so this is where these things start to come into play. And so here I've shown it in a little bit more detail, but this time I've put on the wave functions of each of my vibrational energy levels. So my first line here, the blue line, is showing the absorption of light from the ground state into the excited state. So although I've given you the Maxwell-Boltzmann distribution earlier and said that vibrations might exist in the first excited state or maybe even the second, still most of them are in the ground state. There are a measurable few, but a few in the first excited state. But most of my transition is going to come from the ground vibrational state of my molecule. I excite up, but you can see in this case I've shown the excitation into this V prime is equal to 2 energy level. And basically the strength of my oscillator, the strength of absorption that I see, how allowed my transition is related to the overlap. And I've used this term earlier in the day, and this is terminology, the overlap integral. The overlap of the wave function of the ground state with the wave function at the excited state at the same nuclear distance, at the same reaction coordinates. The bigger that overlap, the more allowed my transition is. The more allowed my transition is, the higher the value of this extinction coefficient will be. So that's one of the factors that's playing into this extinction coefficient value, the overlap integral between the ground and the excited state. So we have an approximation which makes our understanding of this very, very simple. It's called the Born-Oppenheimer Approximation, and it basically says that for the Franck-Condon to work, we basically are treating our vibrational and our electronic transitions independently. But it works in terms of there's not actually a huge amount of overlap between them. So the overall wave function is clearly a combination of the electronic and the vibrational energy level. And because it's a quantum mechanical thing, that won't be easy to calculate, especially when I've got more than one electron. But the Born-Oppenheimer approximation is saying that I can just simply take a simple model of the wave function of the electronic energy levels and a simple model of the wave function of the vibrational levels and combine them and look overall at the overall wave function. And so this is kind of on this Franck-Condon image where I've drawn on these wave functions and saying that I have the overlap integral just between the ground and the excited state. This is actually making use of this Born-Oppenheimer approximation. I am kind of rushing over this in a slight way, but I encourage you to check out the descriptions of it in both Wardle and Wayne if you can. It will kind of explain it in a slightly less hand-wavy situation. I don't want to go into it too much here because my main kind of points I'm trying to emphasize in this lecture is the what are the origins of this extinction coefficient. So I know that my my overlap integral between my ground and my excited state is going to play a part. But what gives me a good overlap integral? So here's the molecule anthracene. I don't have anthracene as my selection, but anthracene is a rigid, kind of planar molecule. It's these three fused rings. It's really quite stuck in its structure. It has vibrations associated with it. They're usually kind of the more breathing modes and the wagging of the hydrogens and the vibrations of the hydrogens. But it's a molecule that it doesn't kind of rotate and change shape and kind of, it's not as dynamic as some of the other molecules we might come across. But one of the things about anthracene is the excited state of anthracene, the structure of the excited state, is quite similar to the structure of the ground state, which means that there is very little shift in the reaction coordinate of my excited state. So the equilibrium separations are essentially the same. That means my vertical transition is happening in virtually the same place on the Morse plots of the ground and the excited state. And so I end up with a very, very strong overlap of wave functions for my my ground state to excited state for the vibrationally 0, 0 levels and for the 0, 1 level. But as I go up, so 0, 4, 0, 5, 0, 6, these overlap integrals are very, very small, because if I kind of think about what's going on in terms of the wave function, well, for my vibrationally V equals 0 level, I've got all of my wave function kind of centered as a Gaussian distribution around the middle of the bond, whereas as I excite to V equals 5, V equals 6, I'm spreading it more diffusely, so that overall the wave function at any point is lower, and it starts to become slightly more focused at the edges of the well as well. So with my anthracene molecule, I here have a spectra of anthracene that I've recorded, and we can see here, we'll notice first off that the absorptions are focused in the UV part of the spectrum. So 400 to 700 nanometers, that's normally what we would refer to as visible. And my transitions are happening, and I can physically see that I've got multiple kind of peaks in this anthracene spectra, and those multiple peaks are actually arising from the fact that I have multiple transitions to the vibrational energy levels within my molecule. We would normally refer to these as vibronic kind of levels, mixture of vibrational and electronic. And so this is kind of playing on the Born-Oppenheimer again, in that I have these, I'm allowing these mixed transitions. You know, they're not obeying our traditional selection rules of V equals plus or minus 1, because it's not a pure vibrational transition, it's a vibronic transition. So here I've drawn it on. The simple way to think about this is, if I have this transition here from my ground, these are all going to be coming from my ground vibrational state that I've drawn on. If I have a transition here from my ground vibrational state to my ground excited vibrational state, I will know that that is my lowest energy transition that I'm going to have amongst the lot, and therefore this is going to be the longest wavelength. So this very first peak that I'm meeting, nice big strong absorption. You can see I've actually got, instead of it being absorption on the side, I've actually measured this in terms of extinction coefficient. So this is, say I'm talking about the smaller extinction coefficient. This is just, I know the absorption and I know the concentration, I know the path length. So I've been able to work out this extinction coefficient. But I have this first transition, ground state, vibrational to excited state, ground vibrational level. This is this first peak. As I increase my vibrational levels, I'm moving the peaks along, and I get a better overlap in this case between my my V equals 0 and my V equals 1 in my excited state, and so I see a slightly stronger. But as I go up, I start to see this coupling dropping off. Now, these shoulders are actually because of some of the material being in the vibrationally excited ground state. So coming from the V equals 1 is the origin of these shoulders that we see. But hopefully that is giving you some idea of the structure of anthracene. Very little change in the structure of the ground in the excited state, therefore very little kind of shift in the potential wells, and the potential wells are giving me where my wave functions are, and it's this overlap integral between my grounds and my excited state, which is giving me the strength of this extinction coefficient. And these are all, I'll just note right now, these are all what I would call spin-allowed transitions. There is no change of spin on absorption of this electron. So for a molecule to be a strong absorber, we want a large overlap integral between the ground and the excited state. So molecules that have a large amount of conjugation will usually give me a strong absorption. One, because their structure is pretty fixed between the ground and the excited state. There's very, very little change. And as there's very, very little change, it means that I'm not kind of moving my excited state orbitals across too much. And so something that is rigid, aromatic, tend to have very large overlap integrals. And if we think back to that structure of the methylene blue, there was a lot of kind of aromaticity in the molecule. So I've just given you some examples of this. We'll meet some of these molecules again later on in the study. But, what do I mean by a large extinction coefficient? So if I just go on the basis of DNA, about 6,600 per mole per centimetre is the value of the extinction coefficient for DNA. There's, quite a few, 3 or 4 double bonds in these molecules, some conjugation between them. It's a pretty big absorption. and so a good value of an extinction coefficient. This TOTO, this is designed as a chromophore. This is a molecule which has specifically been chosen for the colour and the colour intensity. And so it has a massive extinction coefficient, well over 100,000. So molecules which are used as dyes, used as chromophores, will tend to have extinction coefficients at least 50,000, some as high as 150,000 per mole per centimetre. Massive extinction coefficients. And we can use our kind of chemical knowledge to design these chromophores in terms of, wanting the structure, putting in the heteroatoms to make it absorb in the right place, all of these types of things. So here I start to talk about, I've got examples of my potassium permanganate and my copper sulfate. My potassium permanganate, an absorption coefficient of 1800, that's pretty strong. It's not as much as my methylene blue. I don't actually list my methylene blue value here, I'm sorry. It's not as much as my methylene blue, but it's a pretty good absorption. And my copper sulfate is 20. So why is the potassium permanganate so much bigger than the copper sulfate? I finally listed one on the bottom. This is praseodymium trichloride. This praseodymium trichloride is 0.07. That's tiny. So what is going on? Well, I have different types of transition, and I'm not going to go into this too much, but if we think about it, my methylene blue, my organic dyes, they are a singlet to singlet absorption. There's very little change in the structure. They are allowed transitions. My potassium permanganate is a ligand to metal, metal to ligand. I'm not going to discuss the difference here, but it's a charge transfer transition. And it's this charge transfer transition which is giving us this colour. My copper sulfate, though, is a DD transition. And DD transitions are spin forbidden. So I'm not going to talk about things like the Laporte rule, remind you of them next lecture, but most of you will have seen them in terms of your inorganic chemistry studies. But the gist of it is that one of my rules, I've not gone into selection rules hugely, but one of my rules is that I can't have electrons moving within the same orbitals. And this is why the extinction coefficients, things like copper sulfate, are so low. So having allowed transitions, having molecular structures which are very similar, having no change of spin of the electron, will give us very, very large absorption coefficients. Having forbidden transitions, those extinction coefficients are really low. I hope that I've managed to cover some of what was lost in the lecture. I'm really sorry that it didn't record. If you have any questions or you want me to explain any of the material again in more detail, please just let me know.